What if you had to search hundreds of words in a giant grid, instantly? Word Search 2 is a Pattern Mastery 100 Super Challenge and a favorite at Google and Amazon for testing your ability to combine tries with grid backtracking. Over 40% of candidates either time out or overcomplicate their solution. If you ace this, you can handle big data search and optimization. Let's break down Word Search 2 using the basic method, so you can attack even the hardest grid search questions with confidence. Given a 2D board of letters and a list of words, return all words that can be formed in the board by sequentially adjacent letters, horizontally or vertically. The same cell can't be reused in a single word. Input: 2D grid of letters, board. List of words, words. Output: list of strings. All words found in the board. Think about an app that suggests all possible words you can swipe in a Boggle or Scrabble game board. An interviewer might ask, how would you optimize a word search engine that checks for all valid dictionary words in a large letter grid? What's tricky? Checking every word individually with DFS is too slow, needs try optimization. Must prune searches early if the prefix isn't in any word. Handle duplicate word discoveries and overlapping paths. Must manage visited cells and efficiently mark words as found. Think step by step. Build a try with all words. This allows O1 prefix checks, making it fast to abandon dead-end searches, for every cell in the board. Start DFS/backtracking to search for words. At each step, follow the try based on the current board letter. If you reach a try node with a word, add to results. Mark cells as visited, for example, temp set to hash, then restore after recursion, backtrack. If no further try child exists for the path, stop the search immediately. To avoid duplicates, set the found word to none or remove it from try after it's found. Let's clarify. The try enables prefix pruning. Never explore if the prefix isn't possible. Backtracking manages cell visits per word path. Only need to explore directions, up, down, left, right. Edge cases. Board or word list empty. Return. Square brackets. Overlapping word paths. Duplicates in input words, should only report found once. Build a try from words. Loop over each board cell. For each cell, run DFS. If try has no matching child for letter, return. If try node's word exists, add to result and set to none. Avoid repeats. Mark cell as visited. Hash, recurse in 4 directions. Backtrack, restore cell. Collect and return results. Now let's implement the straightforward backtracking approach, checking each word individually by exploring all possible paths on the board. Main find words method, we extract the number of rows and columns from the board. We'll need these throughout all backtracking operations. This list will hold all the words we successfully find on the board. We create a set to avoid adding the same word more than once, since different paths could find the same word. For each word, check if we haven't already added it. Call X to see if the word exists anywhere on the board. If it does, we store it in the result and mark it as found. Finally, return the list of all successfully found words. X method, check if a single word exists. We initialize a visited grid so that during each search path, we don't reuse the same cell twice for the same word. We iterate over every row and every column of the board. We will try starting the word search from every position. If a depth first search starting at this cell finds the word, we immediately return true. If no starting position succeeds, the word does not exist on the board. D method, recursive DFS backtracking. If we've matched every character of the word, the entire word has been successfully found. This line checks all failure cases. Out of bounds, already visited this cell. Board character doesn't match the word's character. If any condition fails, we stop the search from this route. We mark the current cell as visited to avoid reusing it during the search path. We attempt to continue matching the rest of the word in 4 directions. If any direction returns true, that means the path successfully completes the word. We unmark this cell on the way back so it's available for other search paths, a standard part of backtracking. We return whether any of the 4 recursive searches succeeded. And that's how this algorithm works. It first checks each word individually, then brute forces through the board with backtracking to match characters step by step. Efficient for small cases, simple, but not very scalable, yet still elegant in its approach. Let's test our word search function on this board. Each word in the list must be formed by moving through adjacent cells without reusing a letter. Our backtracking explores all valid paths. Oath is found by following OATH on the board. Eat is found across the second row as EAT. P can't be formed because there is no connected path matching the letters. Rain also cannot be formed from adjacent cells. So the words we successfully locate are oath and eat. And that's exactly what the program outputs, matching the expected list. So, our implementation is correct. The search identifies only the words that can be formed on the board. Now let's implement the optimized trie-based backtracking method, pruning dead paths early and collecting valid words efficiently through shared prefixes. We use a trie to store all words, then backtrack once over the board, sharing work across all words. Trie node definition. This defines a trie node n. Each node has an array C of 26 possible children, one for each lowercase letter, and a W string that stores a complete word if this node represents the end of one. If W is non-null, it means a word ends here. Find words, main entry. This method finds all words from WS that can be formed on the board B. We first build a trie from all the given words using helper method T. This lets us search for all words at once while walking the board. We create a list to store all words we successfully find on the board. We read the board dimensions, m rows and n columns. We iterate over every row of the board, and every column. From each cell, we will start a DFS to explore possible words. For each starting cell, I, J, we call the DFS D, beginning from the trie root R. This tries to match any word whose path passes through that cell. After exploring the whole board, we return the list of all found words. T. Build trie from words. This helper method builds and returns the trie root from the list of words. We create the root trie node. It represents an empty prefix. We iterate through each word S in the word list. For each word, we start at the root and walk down, or grow, the trie according to its letters. We break the word into characters and process each one. We compute the index for this character, from 0 to 25. If the corresponding child node doesn't exist yet, we create a new trie node. We move down into this child node, extending the path for the current word. After processing all characters, we store the full word S at the final node. This marks that this path corresponds to a complete word in the dictionary. We return the root of the fully built trie. D. DFS backtracking on the board. This DFS method explores the board starting from cell I, J, and the current trie node N. If a valid word is found along the path, it's added to res. If the coordinates go out of bounds, we immediately stop this path. We read the character currently on the board at I, J. If the cell is marked as hash, it means we already used it in the current search path, so we cannot reuse it. We return. We move down the trie using this character. If this path doesn't exist in the trie, N will become null. If there is no trie node for this letter from this path, then no word can be formed continuing from here. We stop. If this trie node stores a word, we've just found that word on the board. We add it to res, and set NW equals null so we don't add the same word multiple times from different paths. We temporarily mark the board cell as visited by setting it to hash. This prevents revisiting the same cell in this path. We explore downward from the current cell. We explore upward. We explore to the right. And we explore to the left, covering all four directions. After exploring all directions, we restore the original character in the board cell. This unmarks it so other paths starting elsewhere can reuse this cell. And that's how this algorithm works. It first builds a trie of all words for shared prefix checks, then backtracks across the board using that trie to efficiently prune dead paths and collect matches. Efficient, simple, and elegant. Let's test our function on this smaller board. We're checking whether the word APB can be formed from adjacent cells. Although the board contains the letters A, B, C, D, there's no way to form ABAP without reusing a cell, and reuse isn't allowed. Every path eventually fails because the word requires a second B that cannot be reached legally. And that's exactly what the program outputs, an empty list, just as expected. So, our implementation is correct. The search correctly returned big grid, huge dictionary, and we still want instant results. That's the challenge of word search 2. This problem tests whether you can fuse a trie with disciplined backtracking to stay fast and avoid dead ends. Let's do a recap. We're given a letter board and a list of words. We need to find every word that can be formed by walking adjacent cells, no reusing the same cell within a single word. The output is all valid words we can actually trace on the board. Brute forcing each word with DFS is too slow. The key is a trie for prefix checks. It lets us abandon paths early when the current letters can't lead to any word. We also have to manage revisits, overlapping paths, and prevent duplicates once a word is found. Our plan. Build a trie from all words to enable O1 style prefix pruning. Start a DFS from every cell, following the trie as we move. If we land on a trie node that holds a complete word, record it and mark it so we don't report it twice. Use visited marking while exploring, then backtrack cleanly to restore the board. We executed that blueprint. Trie for fast prefix checks, DFS from each cell. Prune immediately when there's no matching child, mark cells during the path, and backtrack to continue exploring. The code ran smoothly without errors. On LeetCode, the solution returned exactly the words present in the board. In the example, it found oath and eat, skipped entries that aren't present, handled duplicates correctly, and passed the test cases as expected. The takeaway: performance comes from pruning. Pairing a trie with careful backtracking turns a massive search space into a set of focused paths, fast, accurate, and interview-ready.